So we talked about frequency in terms of which ranges we are most sensitive to. But is there anything else worth knowing about the frequency of a sound? Well, frequency, it turns out, is a good way to talk about pitch. You've probably heard this statement before, A equals 440 hertz. This literally means that when you play on a piano, for instance, the note A above middle C or A4 for your MIDI types, it'll make a sound that vibrates at 440 cycles per second. That is if the piano has been tuned with a reference of A equals 440 as a starting point. The cool thing about the starting point, or reference, is that in theory all instruments tuned to the same initial reference should be in tune with each other over the entire range of pitches that they can produce. So, how does knowing just the frequency of a single pitch define the pitches of all the other notes? Pitch, it turns out, is a relative thing. Let's think about an octave. If I play a major scale starting at A4, which equals 440, it goes A, B, C sharp, D, E, F sharp, G sharp, and ends on an A. Okay, so technically this ending note is A5, which is one octave higher than A4. But it's still an A. So what's going on? Let's start by looking at the frequency of this A5. If A4 equals 440, then A5 equals 880 hertz. Interesting, right? Okay, so there are two distinct and simple possibilities as to what happened here. Either we added 440 to 440 to get 880, or we multiplied 440 times 2 to get to 880. Remembering that we started at 440 and ended up at 880, let's go up another octave to A6. If the addition method is correct, we can expect a frequency of 880 plus our 440, which equals 1320. If multiplication is the way it works, then we should get 880 times 2, which is 1760. And 1760 hertz it is. These pitches have a ratio, which you get by dividing the higher number by the lower number, because we're going up, of 2 over 1, or 2 to 1. Using this logic, we should be able to predict the frequency of the octave above A6 by multiplying 1760 by 2, which equals 3520, and that would be correct. Going down, we just turn the ratio upside down from 2 to 1 to 1 over 2, or 1/2, so that one octave below A440 would be half of that, 220 hertz. Now, I realize I haven't spoken about the notes in between octaves, and I hear there are some, but we'll get to that in a later discussion. What's important here is that we're able to figure out the frequency of a particular note by knowing the frequency of a starting pitch and applying a ratio. What's more, the ratio between intervals, like octaves, is always the same. So going up in octaves will always be a 2 to 1 ratio, and going down in octaves is always a 1 to 2. It turns out that our hearing for pitch and loudness work along similar equal ratio kind of lines. So sometimes it's not the actual or absolute value of something that counts, but its value relative to a reference point that is important. Like maybe something sounds loud because something else sounds quiet.